All right, that looks like it's working. Okay. So as a reminder for those of you that are actually watching online, this is the makeup lecture for the day of the Jazz Fest that got preempted. Everyone here, of course, was just here for the previous lecture that was going on, but that's why this one's online. So we're starting in a new chapter. We're done with talking about Newton's laws, Newton's 3 laws, and friction. We're going to move to some interesting sort of applications of those laws. And then the last chapter we're going to do before the second exam will be about energy, which is sort of taking forces and taking them to their next logical step. But this next bit is just about forces and sort of taking them, considering them in more complicated cases. Okay, once again, for those of you watching online, a summary of what we just talked about. We're talking about different kinds of friction. Static friction, which operates on bodies that aren't moving, and kinetic friction that operates on bodies that are sliding against one another. Both of them have the form that the magnitude of the forces is equal to some coefficient of friction times the normal force, which is how hard the two bodies are being pressed together. The static friction only goes up to the amount that you're pushing on it, but always acts exactly counter to the forces that are applied to it. And kinetic friction operates in the direction opposite to the direction of travel, so opposite the velocity vector, and is equal to the coefficient of kinetic friction times the amount that are being pressed together in the normal force. And these coefficients are always between 0 and 1, and the coefficient of static friction is always greater than that of kinetic friction. Okay, so today we're talking about this new stuff, chapter 6, and the first thing I want to talk about is motion in a circle. So recall we talked before about what happens when you have an object and it's moving in a circle, right? What force causes it to remain in that circle? Centripetal force, okay? And centripetal force, or centripetal acceleration, is what allows that to happen. And what must be causing that to happen, we're going to call it a force in general, centripetal force. But ultimately, ultimately, this isn't like a fundamental force, right? This is not like a new electromagnetism, new type of electromagnetism or something. Okay, this is just like some force must be acting to keep this thing in circular motion. What is it? And part of what we're going to talk about now is like what are the different ways you can do that? What are the different ways you can make it happen? What are the different ways it will work, and what is causing the centripetal force in any given case. So, as a classic, if sort of boring case, you can imagine, we'll take my Diet Mountain Dew, which I don't have every day, but I wish I had it every day. I need to bring it more often. Has anyone tried the Diet Baja Blast that they have now oh my gosh, it's so enabling for me, okay? Seriously, I'm in a much better mood ever since that stuff came out. Okay, so ultimately, if you try to, hold this can upside down, all of the life-giving liquid will sap away, and it will be very sad. However, if you move it in a circle, and you move it in a circle in the right way, you can have it such that that effective centripetal acceleration, or the centripetal force, will ultimately keep the liquid from spilling out, right? If you move your hand, if you go fast enough, you go around, you can go fast enough that it won't spill. If you go too slow, though, it will spill. I'm not doing that right now, okay? Especially for the people in the front row. So what's happening there? So ultimately then, you're moving the Mountain Dew in a circle. Let's figure out what the forces are on the Mountain Dew that are keeping it in place as it goes around. In order to do this, we're going to fill out a free body diagram for each of these cases, or actually just the bottom case, the side case, and the top case, because the other side case should be the same. They should be symmetric. Okay. So here's the Mountain Dew up here. What are the forces acting on the Mountain Dew in this case? Yeah. Gravity. It's the easy one. Force of gravity, which is pulling down, which should be pulling this stuff out, but it isn't, so we'll figure out what's going on there. What are the other forces? Yeah.
Centripetal acceleration.
Okay, so right, centripetal acceleration isn't really like we said, it's not an inherent or a fundamental force. So what is it then? What would you call
It'd be like the force of your arm.
it? Yeah. So you could call it tension. You could sort of call it normal force if it were, the actual liquid itself. It's the cup or the can that's pushing on it. Let's call it tension. I like tension. So tension is also pulling on it in that case. Okay, in the bottom case, we have the same thing, except now we have a force of gravity that's pulling in this direction, and a force of tension that's going toward the center of the circle. It's going the opposite direction. Whoa. For the side case, we have gravity, it's going this way, and we have tension that's pulling it this way. So in each case, these don't balance, right? In each case, there is some net force on the body. Because there's a net force on it, it is not continuing in motion. It is not staying in motion with constant speed, but rather its speed must be changing. And so this is where the centripetal force comes in, okay? So in order to figure out what the total force is on it, I mean, how do you know what the total force is? I guess we get a force meter and calculate the tension in, between my hand and the can. Or we can say, well, look, we know that if you're moving around, if I was moving this around at a given velocity, v, that in order to execute this simple circular motion, the total acceleration on the can must be equal to the centripetal acceleration, which is negative v squared over r hat, in this case, must be toward the center. So we know what the acceleration must be, just because we can see the motion, we can see how the object is speeding up and slowing down, what the change in its velocity is. If we're going at a constant velocity, then we know this must be the result. And this is where centripetal force is going to come in. There must be some combination of other forces, and we don't know what all those are, but there's some combination of forces that are leading to the total force must be equal to the mass times this centripetal acceleration. So we know that the forces must add up to this in all the cases. Therefore, with the free body diagrams, this is going to allow us to go back and figure out, what was happening there and which was bigger, the tension or the gravity, and what's causing what in each of these particular cases. So let's go back. Let's look at the case at the bottom first, I guess. So at the bottom, total force is equal to, or the force, the radial force toward the center is going to be equal to mg minus the tension. And that's going to be then equal to, at the bottom, must be equal to negative m v squared over r, right? So let's figure out which needs to be bigger in which case. Well, in this case, let's divide through by V, or I'm sorry, by the mass. G minus tension divided by mass is equal to negative V squared over R. In that case, right, if you take the gravity, which in this case is acting in the positive direction, at the bottom, right, this is the direction of R hat, and you subtract off tension divided by mass, in order for that to be negative, in order for there to be a net force at the bottom that's upward to keep this thing in circular motion, there must be, the tension must be greater than the gravity, right? The total tension force must be greater than the force of gravity. So that means that as you're swinging this thing around, down here at the bottom is where the tension is greatest, where you're having to pull on it the most. Because not only, if you're in space, on the space station, putting this thing in a circle, right, it would be constant all the way around. But here, in addition to providing that centripetal acceleration, that centripetal force, the tension also has to counteract gravity when it's doing that. So the greatest tension on the system is going to be when you're at the bottom. Let's look at what happens when you're at the top. When you're at the top, the radial direction is switched. Now radial direction is outward, but in this case it's up. And in that case, the net force is equal to negative, look at our diagram here, both of these are downward, so both of these are negative. It's going to be negative mg minus the tension, and that still needs to be equal to negative mv squared over r. Going through by negative m, you get that g plus t over m is equal to v squared over r. So in this case, the total centripetal acceleration is provided by two things. It's provided by the gravity, but it's also provided by the tension. They're both working together, and the sum of those two at the top is what needs to provide the total centripetal acceleration to keep you in circular motion. So this works up until the point where this centripetal acceleration becomes less than gravity. If this centripetal acceleration becomes less than gravity, then the tension is negative, right? And then you're pushing out on the can when it's at the top. What would happen at that point? Yeah. You're pushing up on the can, but you ain't pushing up on the liquid. The liquid is going to fall out due to gravity. Therefore, when thinking about this problem, in order to not spill the Mountain Dew, what you need to do is to spin this thing fast enough so that gravity is providing exactly the right amount of centrifugal or centripetal acceleration at the top there, and that tension is equal to 0. Right? Because if the tension is negative and you're pushing outward, then bad things happen, it spills. And if the tension is contributing, that's fine, but it's unnecessary at that point. The critical speed, then, it's the gravity that's providing the centripetal acceleration at the top. Okay, so in that case, the tension is 0. And so going back to our equation up here, in that case, gravity needs to be equal to v squared over r. V squared would need to be equal to r times gravity, or the velocity would need to be equal to the square root of r times g. Does that make sense? So what are the units of gravity? Meters per second squared. The units of r, which are the radius of the circle, is going to be meters. So this could be meters squared per second squared. When you take the square root, you end up with meters per second. So that ends up as velocity. So that, at least fundamentally, makes sense. Okay, so in my particular case, my arm is, say, a meter long. So if r were equal to 1 meter, gravity is equal to 9.81. The critical velocity is going to be equal to the square root of 9.81 meters squared over second squared, which is going to be 3 point something meters per second, 3.1, about pi. Everyone knows the square root of 10 is pi, right? 9.81 square rooted 3.13. See? Pretty close. Okay. 3.1. I think I only measured my length of my arm to the nearest tenth of a meter, so I'm going to give this 2 sig figs. 3.1 meters per second. Therefore, is how fast I would have to move around in order to be able to get that just barely right. So if that were true, it would take me 2 seconds to go around the whole circle, right? Because the whole circumference of a circle of radius 1 is 6.28. So gosh, well, I don't know if we can do that and not make a huge mess. So about, yeah, that's, okay, I'm not going any slower than that. But that's about what the critical velocity would be. See, now I'm really worried about my sig figs. What if my arm is really, this velocity needs to be faster the larger the radius, right? So what if my arm were really 1.2 meters in size? I could totally spill then if I only went 3.1 meters. So let's not do that. I'm just going to go that fast, and we're going to call that good. Okay, so in that case, this is the minimum speed you'd have to go, and any faster than that, of course, is fine. The tension will provide the rest. Any slower than that, things break down. And so that is actually the source of this fiendish device, which we're going to use for a demo. So this does the same thing effectively as me doing a circle with much less probability of requiring a mop at the end when things fail. So what this track does, right, is you just put a marble on the track, and it's going to fly around, and it's going to have the same restriction that we just had, right? In that at the top, in order for the marble not to leave the track, it must be going fast enough that it's still pushing outward, or that the track itself is pushing inward and providing some of that centripetal force. And the critical event would be gravity is just barely keeping it in place, keeping it in that circle. And any slower than that, and it should leave the track and fall out. So how fast should it go? Let's calculate that. We just said that critical velocity is the square root of r times g. All right? What do you suppose the radius of that is? 20 centimeters? We gotta get this right, guys. Otherwise, we're gonna spill it all over everywhere. Okay, that seems excessive, but I suppose we could do that. We want it to be accurate at some level. Yeah, I know I had one of these. There we go. I've used this before and had mixed results personally. So let's see. Oh, I said I need to mark these points. Okay, got it. This is really excessive, people. This is like, welcome to the future, where the best way you can think of estimating how big something is to break out your phone. Okay. Okay, tragically, it has an answer in inches. It thinks that's 25 inches. No, it's not. You couldn't tell that I was pointing at the back. Okay, let's see. I'll try one more time. I still think it's 20 centimeters, and we don't need to do this, but okay. There we go. Now it says it's 12 inches, and I think it's more than that too, so I'm not believing it. All right, let's go with 20 centimeters, in which case that velocity needs to be the square root of 0.2 meters times 9.81 meters per second squared, which is going to be the square root of 2, so this would be like 1.4 meters per second, yeah? (9.81 times 0.2). Something does not look right, I'm gonna have to say. Times 0.2, yeah, that looks good.
Divided it by 0.2.
9.81 times 0.2. See, this is why I have you guys here. Okay. That looks better. See, I did it better in my head. All right, 1 point. See, I was totally right in here. Totally necessary. Okay. 1.4 meters per second is how fast it would have to go. So, how high do you suppose I would have to go before this is going to be making sure it's going at least 1.4 meters per second? We can calculate it once we get to the energy section, but that's kind of in the future. So I'm going to cheat, right? You can imagine the higher you start here, the faster it will be going by the time it gets through there, okay? So according to the mark that someone has cleverly left on this should be the minimum height at which it would go. Let's start at the higher height. So this should work in principle. It should go around and be able to stick to it. Okay, that wasn't bad. They look pretty close though. I don't know if we can go a whole lot lower and have this work. They say this is the minimum. Let's see. Okay, I think that's less than the minimum. So according to that, if we go even faster, it should easily stay on the track. Actually, it should probably fly off. Okay, that's not bad. And the lower we go, so effectively this height limit corresponds to a velocity limit, right? So the higher we go, the faster it's going. At some point, if we go any slower, then it's not going fast enough for gravity. The amount of gravity exceeds the amount of centripetal acceleration it needs, and therefore it departs from simple circular motion and starts to slide down. It was close to the limit. So someone put a number down here that is just not right. How about this one? That's getting right when you're doing it. Okay, so this is sort of the same problem. We're looking at that circular motion. We're trying to figure out what's going on. Let me circle back real quick to the part we didn't talk about, which is what's happening at the side. Now, I'm not going to do any calculations about this, but let's just think about it. What happened at the side here, we have these different forces. We have the force of gravity. Sorry. Over here, we have the force of gravity. We have the force of tension. In this case, the gravity really isn't contributing at all to the centripetal force, right? Or to the centripetal force. It's only the tension. The gravity, in fact, is pulling it downward. So this is actually a case where our assumptions break down. I assumed simple circular motion where the velocity was constant. If you were to actually let this go in this exact way, the velocity wouldn't be constant, right? You'd be speeding up as you're moving downward. You'd be slowing down as you move upward. Furthermore, if you were to try to remain in simple circular motion, you could do it, but you'd have to have an additional force this way to counteract gravity. So that's what my hand does as we're moving around, right? It's pushing upward to slow it down as it goes through here. It's pushing upward again to speed it up as it's going on the upward track. So we'll talk more about exactly how those speeds are going to vary when we start talking about energy, but we don't have to quite get into that technical bit just yet. Okay, let's advance. Let's do a problem. Okay, this problem, that one's super hard. It asks in a dryer that's rolling around, at what angle along the dryer do the clothes fall? Let's not do that one unless we have lots of time, because that one's fun, but tricky. Let's do this top one to start with, which says that Tarzan tries to cross a river by swinging on a vine. The vine is 10 meters long. And his speed at the bottom of the swing, just as he clears the water, will be 8 meters per second. Tarzan does not know that the vine has a braking strength of 1,000 newtons. So the question is, does he make it across the river safely? So how do we calculate that? What should we do first? Draw a picture. Yes, good, good. So this is 6.15, was it? 6.15, okay. And the question is, does Tarzan make it? Let's draw a picture. We've got the two banks of the river. We've got the river in between. We've got a tree with a branch that's happily hanging over the river here. And from there, it has a given length, and it's going to swing across. This length, it said, is 10 meters. Okay? It says the velocity at the bottom here is 8 meters per second. That's pretty fast. All right? And what else is the other relevant number? That Tarzan's mass is 85 kilograms. Okay? What's the next step toward figuring out if he's going to make it? Free body diagram, yes. See, it's not that hard. Okay, draw a picture, then draw a free body diagram. At the bottom here, what are the forces on Tarzan? Gravity. Yep. And? Tension. In the string which is pulling him upward. Okay? Assuming that he were to make it, let's say he were to make it, okay, this is going to be the force, point of, the greatest tension. Then the sum of those forces must be equal to the centripetal acceleration times the mass, or the centripetal force that's keeping him in this circular motion along the vine. So that must be equal to his mass times the centripetal acceleration, which is v squared over r. Yep. And v squared over r is the total force. So that must be equal to this sum of the forces that he has here. So mv squared over r in this case is going to be in the upward direction. So that's going to be equal to the tension minus the force of gravity. Measuring those both in the upward direction. Okay, so let's fill that out. mv squared over r must be equal to tension minus the force of gravity. So mv squared over r must be equal to the tension minus mg. Ultimately, we want to find the tension. I want to know what tension would it require for him to make it across. And we'll compare that to the value that the actual tension of the vine and see if it's going to work. So let's solve this for t. Tension then is going to be equal to m v squared over r plus mg. So let's go ahead and calculate what the centripetal acceleration v squared over r should be. It said that his velocity was 8 meters per second. So we'll square that. Divided by the radius, which is 10 meters. What does that equal? 8 times 8 is 64, divided by 10, it's going to be 6.4. So this is going to be 6.4 meters per second, right? We lost 1 meter. There's 2 meters per second squared. So that's an acceleration. So m times, pulling the m out, 6.40 meters per second squared, plus gravity, 9.81 meters per second squared, should be equal to the tension. So that's equal to m times 16.21 meters per second squared. Yeah. The mass is 85 kilograms. Where does that come up? I think it should be 1,300. 1600? Looks bad for him. Okay, 16.21 times 85. 1378, but this really only needs to have 3 sig figs, right? Because the mass is only 3 sig figs. This is in newtons, so this must be 1.38 times 10 to the 3 newtons, or 1.38 kilonewtons, you could also say. Okay? It says that the breaking strength of the vine is 1,000 newtons. Therefore, oh, question, yeah.
Couldn't you also write it as 1,380 newtons?
The problem with that is if you write it as 1,380 newtons, does that have 3 sig figs or 4 sig figs?
I mean, I think it's got 4, but sometimes the website allows you to do that.
Yes, I think you're right. WebAssign allows you to do that. Don't do that on the test. Because WebAssign assumes that trailing zeros do not count. In that case, what if it were 1,300 newtons but with 3 sig figs? Then you really have to write it out in scientific notation. But I think you're correct. WebAssign will take 1380 for this. But if the correct answer were 1,400, then WebAssign wouldn't take that. And you'd have to write it out as 1.40 times 10 to the 3, or 1.40 kilonewtons. Yep, no, that's a good question. Okay? Yeah, so that's greater than 1,000, right? So, yeah, he's not going to make it. This is the point of greatest tension. At some point before this, he will fall into the water that are hopefully infested with piranha to keep this interesting. Okay. Let's do another problem. That's for Monday. Well, this one looks funner. Let's do this one that I wrote up, because it's a planet problem. Okay. Charles Darwin, of course, first proposed the theory of evolution. His son was an astronomer, though. And one of the things that George Darwin, his son, thought about a lot was the formation of the moon. He was trying to figure out where the moon may have come from. And George Darwin had a couple of interesting ideas, interesting hypotheses regarding the formation of the moon. We now think the moon ultimately formed via a collision early in Earth's history. In the formation of the solar system, we have planets and planetesimals flying all over, and the way they grow is that they crash into each other and they agglomerate into bigger and bigger bodies. So the last thing that smacked into Earth was a Mars-sized planetesimal, about 1/10 the mass of the Earth, and it happened to hit sort of edge on, such that it kicked out a bunch of debris into orbit that ultimately formed the moon. And the reason we think that is actually that there's a large, relatively large set of constraints. For instance, the moon isn't in a perfectly circular orbit that's above Earth's equator. It's tilted a bit. The moon has like no core. It has no metal core. How could you make a planet without a metal core? If you just take average solar system material and just slam it together, it's going to have a metal core. How do you get rid of that? Well, in this scenario, it's because this collision only threw off debris from the outer portion of the Earth, which was already metal poor. The oxygen isotope ratios, it turns out, on the moon are really close to that of the Earth. Whereas you look at the ones from Mars, we have some meteorites from Mars and some other meteorites, the isotopic ratios are whack. They're totally different. They're clearly from a different source. The moon is also almost entirely devoid of water. Once again, if you take average solar system material and you throw it together, it should have some water. But this collision was rather hot, and so it baked off any water in that debris disk. Anyway, but George, when he was back thinking about this problem in the late 1800s, didn't have the benefit of knowing the lunar isotope ratios because he hadn't landed on the moon and brought rocks back like we have, okay? So he was trying to think of how the moon may have formed, and one of the ideas he came up with was fission. So what if you started the Earth, and then, like a Globetrotters player, you spun it up faster and faster. Eventually, you'd spin it fast enough that in order to remain in circular motion, right, what keeps you in circular motion around the Earth? The force that ultimately does that job is gravity. Imagine you're standing at the equator to make the problem a two-dimensional problem. If you're standing at the equator, part of the gravitational acceleration, 9.81, goes toward keeping yourself in single circular motion. You can imagine that if you take the Earth and you just spin it up, you spin up faster and faster, eventually there would be a point exactly at which gravity was providing, all of gravity was being used to keep you in that simple circular motion. All of gravity was providing a centripetal force, keeping you rotating around the center of the Earth. And at that point, if you were to spin Earth even a little bit faster, you would go flying off the surface of the Earth because you'd be moving too fast to remain in circular motion, that gravity wouldn't be enough to be able to keep you in that simple circular motion, and therefore your inertia would start to run off and you'd fly off of it. So let's calculate how fast the Earth would have to be rotating in order to make that happen. Okay. Okay, we're first going to draw a picture. So we're looking down the North Pole. Here's the Earth. Which way does Earth rotate if you're looking down the North Pole? Does anyone know? Counterclockwise. Counterclockwise, correct. Earth rotates counterclockwise if looking down on its North Pole. That way, right, if the sun were over here, then the sun would rise in the east as you go around. That's what we want. So there's going to be some critical velocity here such that U, let's do a free body diagram on U. This is simple enough in that there's two forces. There's the force of gravity, and that's it. This force of gravity, and then there's the normal force, I suppose. In the case where Earth were spinning right at its breakup speed, right before it might fission off material that might go off and form a moon, this normal force would be equal to 0. And in that case, the force of gravity would be equal to the centripetal force entirely. Okay? What is the force of gravity on U equal to? Yep. Well, m times a, so m times g. We'll leave it at that for now. What is the centripetal force necessary to keep you in circular motion? mv squared over r. Okay, so you set those equal to one another. mg is equal to mv squared over r. First of all, what do you notice is true?
The m's.
Yeah. Mass is irrelevant. This breakup speed is the same for all objects on the outer part of the Earth, no matter how big they are. And when you solve it, you find that the limit here is the same one we got before, root rg. Okay, what's the radius of the Earth? 6,378 kilometers. I know this. The gravity of the Earth is 9.81 meters per second squared. Okay, danger, Will Robinson. I've got two different units here. Let's take this as 6.378 times 10 to the 6 meters to keep this in the same units. Because if you multiply meters times kilometers, bad things are going to happen for you. So let's stick it to that, in which case we find that R times G is equal to 6378000. Those are enough of those. Times 9.81. And take the, take the square root of that. And we get 7,910 meters per second, or 7.91 kilometers per second. That's fast. In fact, how fast is that? That's exactly orbital velocity. This is not a coincidence. Okay? If you're in a low orbit around the Earth, you are in an orbit for which gravity is providing in the entirety of the centripetal acceleration. and such that the space station in low Earth orbit is moving at about 8 kilometers per second, exactly this velocity, and that's how it maintains that orbit, that circular motion, simple circular motion. Okay, if the Earth were rotating at 7.9 kilometers per second, how long would a day be? How can we figure that out? Yeah.
Find the circumference of the Earth and then divide that by
Yep.
velocity.
Yep. So we'll take distance equals velocity times time, right? And so we'll solve for time, distance divided by velocity. What's the circumference of the Earth? It's 40,000 kilometers by definition. The meter is defined as 1/10,000th of the distance between the equator of the Earth and the pole. 1/10 millionth, I guess. So a kilometer is 1/10,000th of that distance. By definition, that's like how they invented the meter. They were trying, this happened during the French Revolution in the early 1800s, when all the different principalities in France had different weights and measures and different lengths that they would use. And so it became very difficult to like sell your wares to a neighboring town because they had totally, I mean, how much are you selling? They had a totally different definition of weight or of mass or of distance for how long your rope was or something. So the initial instinct, of course, would have been to have the king impose the correct answer upon everybody. But this being the time of the French Revolution, when kings were typically in two pieces, they decided that, well, they could take the Parisian standard and try to enforce that on everyone, but that probably wouldn't go over very well. So instead, they tried to invent an objective standard for weights and measures, and that is where the entire metric system came from. The idea was, oh, there shouldn't be just some meter stick stuck in some cave in Paris that defines how long something is. Usually anyone should be able to calculate the meter based on any just normal physical parameters that are out there. So they decided that, oh, we'll use the Earth as our standard, and if you measure the distance between the equator and the pole, that would be 10,000 kilometers by definition. It happens that, well, it matters where you measure the distance between the equator and the pole. It turns out Earth is kind of lumpy, and it doesn't work out quite as well as you'd hoped. But we're still stuck with that meter today, such that 1/4 of the way around the Earth is 10,000 kilometers. Therefore, the entire way around the Earth is going to be 40,000 kilometers. Divide that by 7.91 kilometers per second, and we ought to get a rotation period in seconds. It's going to be like 5,000, right? 40,000 divided by 7.91 is 5,056 seconds. This only has 3 sig figs because we're stuck by 9.81 actually, which is holding us back. So this is 5.06 times 10 to the 3 seconds. Let's divide by that by 3,600. That's 1.4 hours. Okay, so if the Earth spun every 1.4 hours, you could fission off a moon. We know this isn't happening, and we'll get to that later in the semester. The reason we know is you take the total angular momentum of the Earth-Moon system, and you all slap it together, the original rotation rate of the Earth would not have been this fast. So this is definitely ruled out. Not to mention that it's not clear how we would actually take the Earth and then start spinning it up to go faster and faster in order to fission off parts. So despite that physical problem, if you just look at the total amount of angular momentum in the system, there's totally not enough to do this. However, oddly enough, in the last couple of years, we have found cases where this is happening. It turns out that asteroids are little chunks of rock typically orbiting between Mars and Jupiter, but they don't have to be. They can be anywhere in the entire solar system, depending on where gravitational encounters with the planets have flung them. But we think of our mental picture of asteroids, we call them rubble piles. So imagine like a giant pile of rocks, of cobbles, and they're just loosely held together by gravity. So it's not like a chunk of rock that has strength, right? It's just sort of just a pile of rocks that happens to be loosely held together by gravity. If you were to take one of these asteroids and gradually spin it up, it too would reach the point where the gravity was providing all the centripetal force, and beyond that, it would start to toss bits of rock off of its equator out into orbit. And we think we've actually seen this places where this has happened. We see asteroids with the moon, and what's happening is somehow these asteroids are being spun up. And you don't need to know this, but what's spinning them up is ultimately sunlight. Ultimately, these things are a little bit irregular, and the amount of sunlight that falls on them and corresponds to where their hottest part is. Photons that get emitted by hot objects have momentum. I mean, not very much, but if it's working over 4 billion years, it is time, okay? It helps you. And so we have these asteroids that seem to have been spun up ultimately by uneven solar heating. And as they do, they start tossing material off. So ultimately, although he was fundamentally wrong about what he was trying to solve, the answer he was trying to solve, which was the formation of the moon, George Darwin's question about how to form moons in general, it turns out we have gotten an answer where that is true, and that's for these little asteroids, which is kind of unexpected. Okay, so here's my summary sheet. Here we go. Okay, so we talked about today, or whenever you're watching this on Friday, we talked about circular motion and forces, wherein, just like there's a centripetal force that was equal to v squared over r, if an object is in circular motion, there must be some sum of forces that equal to the centripetal force, which is mv squared over r. But remember, this is not a fundamental force. You can't say, oh, what's the force? Oh, well, it's mv squared over r, because that's what the centripetal force is. That must be a combination of other forces, be it tension in a string, or gravity, or normal force, that is providing that mv squared over r. So the way you use centripetal force is, if an object is in simple circular motion, you draw a free body diagram, you figure out what the sum of all the forces is equal to, and then if it's in simple circular motion, you know that sum must be equal to mv squared over r, and you set those equal in order to be able to figure out what those forces were in the first place. Okay, well, enjoy the Jazz Fest on Friday, and we will see you next Monday, where we will talk more about interesting applications of Newton's law. See you then. Thanks, guys, for sticking around for the second lecture. I really appreciate it. Plus, now you don't have to watch it on YouTube, so there's other bonuses.